Hello, welcome to another module in this massive open online course, and in this module we will change tracks and start looking at a different topic and an extremely important topic in understanding the performance and behavior of communication systems, which is termed as information theory. Okay. So, as I have already alluded, this is going to be very fundamental, and it is one of the fundamental milestones in understanding the behavior and in also designing better and more efficient communication systems. So, this is termed as information theory. Many of you must have heard of this at several different settings, correct. So, information theory, and as I have said, information theory is fundamental. It is something that is very fundamental to understanding and characterizing the performance of and in fact information theory is not only, although originally intended to study communication systems, it has evolved to encompass a variety of applications such as economics, probability, stock markets, investing and so on. So, the applications of information theory are vast and ubiquitous, all right. However, in this course, as part of this course, we will restrict ourselves to the fundamental concepts in information theory and the relevant applications in the context of communication systems. Okay. So, we are going to change tracks, as I have said, and start studying information theory, and basically to describe information theory or the relevance of information, let us go back again and look at the structure, the fundamental structure of a digital communication system, which we have looked at in one of the very first lectures. So, we have in every digital communication system, we have a source, and the source produces messages which are led to an encoder, correct. So, I have a source, I have an encoder, the source produces message signals. So, the source produces message signals, so the source produces message signal and the encoder encodes them into a stream of bits, as we have seen before, encodes messages to produce. So, the encoder encodes message signals produce a stream of bits, all right. So, we have shown here a typical stream of such bits. Okay. Now, the question is, obviously these bits are going to be transmitted over the channel. Let us look at it, let us take a simple example. So, the bits are going to be transmitted over the channel, naturally that requires bandwidth, right, that requires usage of the channel, all right, and technically one would like to minimize the usage of the channel. So, for a given amount of resources for transmission, let us say in terms of the channel bandwidth or the time, one would like to transmit, well, the maximum amount of information, or one would like to remember, communication is all about conveying information over a vast distance, right, from point A to point B, or even in a broadcast kind from point A to several points, right. So, typically we are interested in conveying the maximum amount of information using the minimum number of resources, or to put it other way, we would like to have a minimum number of bits which signify the channel uses, the number of times we have to use the channel. So, we would like to have a minimum number of bits encompassing or encapsulating a encapsulating the maximum amount of information. Okay. So, so that is the motivation. So, typically we would like, so how many bits, so how to, so typically we would like convey the maximum possible information using minimum resources such as time or bandwidth. Okay, purposefully being a bit abstract, which implies we would like to encode the messages, okay, which implies we would like to encode or represent each message using the fewest possible number of bits, right. In other words, we would like to compress a lot of information into a very few number of bits, and information theory is nothing but a systematic study to enable us to do this, enable us to compress or enable us to represent a large amount of information in very few bits or in very few which thereby utilize very few channel resources, thereby conveying information efficiently using as few resources as possible. Okay. So, essentially, so for that, so this is what information theory enables us to do. Information theory enables us to precisely do this. Precisely do this, that is represent maximum information using very few, or basically maximize information per bit. You can also say that maximize information maximize the information content on a bit by basis, maximize the information content per bit. Okay. And now we all know, we are very familiar with how to characterize aspects, physical aspects such as or let us say characterize, let me be a bit more explicit, characterize physical attributes such as, you know, the weight of an object, the height, for instance, the volume, etc., several other aspects. But how does one characterize something abstract as information? Okay. So, these we are familiar with. So, we are familiar with how to characterize the physics, but how does one characterize something abstract such as information? Correct. Such as the information content. For instance, every day we are exposed to several sources of information, right, from personal communication, from watching, for instance, let us say sources such as the TV, sources such as broadcast media such as the TV or newspaper, or several other sources from our day to day communication, or what we, or through hearsay or so on. So, through a variety of modes we access a lot of information, but we never really stop to think about how does one really capture the information content. For instance, when you see a piece of news, we intuitively feel that some news, right, carries more information than other kinds of news, or some kind of communication has more information, or when a particular person is speaking, he typically conveys more information than someone else is speaking. So, how do you characterize something that is something that you cannot feel? How do you characterize something that is as abstract as information, which is tremendously useful? And information theory does nothing but provide us with a means to the tangible, a means to characterize, to provide us a tangible measure of this otherwise abstract notion of information. Okay. So, that is what information precisely does. Okay. Information theory is nothing but provides tangible measure so that you can precisely characterize what is the information of one source versus the other. Okay. So naturally, information content of a source, so naturally, and this provides us a mathematical framework. Okay. So, information theory is a mathematical framework. We are talking about not a qualitative, but a quantitative framework rather. Okay. We know qualitatively what constitutes more information. Okay. It is an objective measure or a mathematical framework, or you can also say as an objective measure removed from personal perception. That is the important aspect, because different people might feel that the information content is different, and more importantly, this is a mathematical framework or a numerical framework, or it is a quantitative framework. Okay. Not just simply a qualitative framework, but a quantitative framework. And central to the notion of information theory, if you look at information theory, central to the notion of information theory is the concept of a source of information. So, we think of information as being generated as by a source. This source can be several things. For instance, can be people who generate the information, or things such as a next higher layer, such as a source such as, for instance, the internet, or source such as, for instance, the TV, from where you find information, right, which basically conveys information in some sense to you. Alright. So, there are several sources which generate the information. Okay. For instance, when you are talking to your mobile phone, it is a human being who is generating the information, which is later encoded, which is later the voice, which is digitally sampled and encoded and converted into bits. So, there are several sources of information. Okay. And now, information theory, as we have said, is a mathematical framework to characterize the information generated, the average, what is the information of a source. So, we also talk about what is the information. It can be a physical, it can be a living object, information, or information generated. What is the information generated? We talk about this. Information generated by a source. What is the information generated by a source? So, we would like to characterize the information generated by a source. Okay. So, let us typically consider a source. As we have said, a source generates messages. Okay. So, the source, let us say, generates let us say generates symbols S0, S1, so on up to Sn minus 1. In fact, this is a discrete set of symbols. So, you can also call this as a discrete source. They can also be continuous source. Okay. Continuous sources can also exist, which we will deal with later. So, discrete source implies generates a set of discrete symbols. Okay, generates a set of discrete set of symbols. Which generates a discrete set of symbols. For instance, this S0, S1 up to Sn minus 1, this is the symbol set. Okay, this is the and this is also termed as the source alphabet. This set is also termed as the source alphabet. So, we have a set S consisting of symbols S0, S1, Sm minus 1 generated by the source. This is also termed as the source alphabet. So, this is also termed as a source alphabet, and further the source is generating these alphabets, these various alphabets at various time instance according to a certain probability distribution, right, according to a certain probability. So, if it is a continuous source, it generates a continuous, it takes values from a continuous range with a probability density function. Okay. Now, we have a discrete source which is generating discrete symbols according to a set of probabilities. Okay. So, the symbols, this is the system model, or this is the model of our source which is generating according to a symbols are generated according to a probability distribution. We have probability of the symbol S naught equals P naught, probability of the symbol S1 equals P1, so on and so forth. Probability of the symbol Sm minus 1 equals Pm minus 1, and naturally it goes without saying that from the axioms of probability, obviously these satisfy the axioms of probability. From the axioms of probability, again I urge everyone to revise their knowledge, or revise the concepts of probability and random variables. We must have each pi greater than or equal to 0, each probability has to be greater or equal to 0, and the summation of all the probabilities belonging to the source alphabet has to add up to 1. So, all the probabilities have to add up to the 1. Now, let us come to the concept of the information content of a symbol Si. The let us come to this concept of how to characterize the information content of a symbol. How to characterize information content of a symbol, or basically how to characterize the information content of a symbol, and for that we are going to define the information of symbol SI. ISI, this is basically your information of symbol SI. As log to the base 2 1 over the probability Si equals log to the base 2 1 over Pi, okay, 1 over Pi, and there is a unit for information, the unit is bits. Okay. So, we are defining, this is a very interesting, and this is one of the fundamental definitions in information theory. We are defining the information content, which we said is not very clear, or which is a rather abstract quantity. So, the information content of a symbol. So, this is the definition of information content of a symbol. Now, observe something very interesting. First of all, I will talk more about this definition. I will definitely talk a lot more about this definition as we go through the various other aspects. But firstly, observe, the most important thing is that the information of the symbol has nothing to do with how the symbol itself is represented SI, rather it has everything to do with the probability Pi of the occurrence of the symbol. For instance, the symbol can be a word, the symbol can be a voltage level, the symbol can be for instance such as an event. So, it does not have anything to do with that particular symbol, but it basically deals with the probability of occurrence of that symbol. Alright, and that is the important thing to observe. So, it depends, ISI, the information of the symbol depends on the probability of occurrence of the symbol. Depends on the probability of occurrence of the symbol. Further, you will observe further ISI is proportional to 1 over pi. It's not proportional to pi, it is rather proportional to 1 over pi. ISI is basically log to the base 2 1 over pi, which means if pi tends to 0, if pi tends to 1, that is it occurs very frequently, I of Si tends to log 1 to the base 2 equals 0. If pi tends to 0, then ISI tends to infinity, and this is a very important aspect. It shows that lower, that is symbols which have which have a lower probability of occurrence have much higher information associated with them. So, symbols or events which have a very low probability of occurrence have much higher information content associated with them. Okay, so that is the important takeaway point from this. So, symbols or events with very low probability of occurrence have higher information content. So, symbols which have a very low probability of occurrence have much higher information content, and so therefore, rarer events which are rarer, which are very low probability, have higher information, correct. So, example, right, rare events, rare events have higher information. Think about, for example, news. The news coverage is focused on such rare events. For instance, if an event occurs on a daily basis, for instance such as a local happening which occurs on a daily basis, that is not, things such as that are not covered in the news, because they do not constitute, typically we know intuitively that they do not constitute much information. So, events which occur very rarely, such as happenings on a national scale, or let us say such as happenings on a national scale, or calamities, right, more prominently calamities deserve a lot. So, calamities attract a lot of attention, alright. So, coverage of such events, right, such rare events which do not happen very frequently attract. So, the rarer the event, the more information it contains. So, events which occur very frequently contain less information. In fact, you can think of even sensational events, such as events which do not occur, events which are against the norm, events which are against the convention. Such events are associated with a large information, a lot which are said to deserve a lot of attention, because they have a large amount of information. So, for instance, the other aspect is, you can think of sensational events. The very definition means that against these such events are against the practice, these are unprecedented or unconventional. Or unorthodox. All these basically carry more information. and attract a lot of attention, and therefore attract a lot of attention, or warrant or attention, so as to speak colloquially, make our heads turn because they seem to carry a lot of information. So, the most important aspect, correct. So, I would like to summarize this by saying once again that these rare events or sensational events, events which are rare, right. So, these rare events, which means and we are using this 1 over pi, we are saying that the rareness of an event or the relative infrequency with which an event occurs is proportional to 1 over pi. This is a measure of 1 over pi is a measure of the frequency. 1 over pi can be said as a measure of the relative infrequency. Such, or basically 1 over pi is large implies frequency or events are infrequent. Implies such events are infrequent and therefore carry a large amount of information. Okay. So, what we have seen in this module is basically we have started with a very high level introduction to information theory. We have motivated this feed with this area of information theory, what is the relevance of information theory, and we have basically started with a brief description of the system model and the setup of information theory. Also characterized a fundamental definition of the information content of a particular alphabet belonging to the set belonging to the source alphabet of a source. We will start with this definition and further keep refining it progressively and look at various other norms, various other measures to characterize the information content of a source and the relevance of all these aspects and the relevance in fact of this whole area of information theory in communications in our future modules. Thank you very much.